everyone, welcome to the next episode of my science podcast. Today I'm delighted to welcome Dr. Matthew Middleton, who is a Councillor of the Royal Astronomical Society. He has been a PDRA at Durham, a Marie-Curie Fellow at the University of Amsterdam, and STFC Ernest Rutherford Fellow at Cambridge, and is now an Associate Professor at Southampton. His research focuses on the nature of accretion onto compact objects, and he is an external collaborator for e-ROSITA and head of SMARTnet, which is a network for performing observations of transients, including binaries, AGN, TDEs, etc., simultaneously in multiple wavebands. So thank you so much for joining me today.
My pleasure. Thank you very much for having me on.
So I guess to begin with, may you tell us about your career so far and how you got to where you are today?
I think most of this can be traced back to watching Star Trek: The Next Generation when I was a child. I think most people who get excited about astronomy can either trace it back to something like that or Doctor Who. And I'll be completely unashamed to say that was probably had an important role to play. So I went to Durham University as an undergraduate. It's a wonderful city, ever so small. And I was very fortunate to be surrounded by wonderful people, had fantastic lecturers, and I enjoyed it so much that I stayed on and did a PhD with my supervisor, the wonderful Professor Christine Durham, who is a close friend and is a fabulous, fabulous scientist. And I worked on black holes. And I think it's safe to say that within the breadth and depth of astronomy, very little is as exciting as a black hole because they're so extreme, these mathematical curios. And so I stuck with it. So I did this PhD, and it was, PhDs are wonderful. I know you're not quite there yet, Martha, but one day I hope you will be. And I had a fantastic time. So much so that I stayed on to do a postdoc, a PDRA in Durham. And so I didn't see the sun for like 11 years. Durham is very northern and it's bloody cold and wet. I had a wonderful time. And then eventually I did have to leave. 11 years was enough. And I went to Amsterdam as a Marie-Curie Fellow. And that was great. So that was my first fellowship. I had absolute freedom, except it's only a 2-year fellowship. So it's a bit of a poison chalice. You get there immediately, you have to really ramp up your research to get the next position, which I did, and that was in Cambridge, working under Professor Andy Fabian, who is one of the most important astrophysicists of his generation, a brilliant guy. And I obtained the Ernest Rutherford Fellowship when I was there. Just before I got the ERF, I got made lecturer in Southampton, so there's a bit of finagling to be done, and eventually I ended up in Southampton, and I've been there since 2016. And the biggest change has been that my balance between the amount of research I can do versus my teaching has completely shifted. And so I now teach about 150 undergraduates a year. I have PhD students and lots of different administrative tasks. I'm lucky enough to be a councillor for the Royal Astronomical Society, so I contribute to the policy of astronomy in the UK. And it's very interesting how you go through your career and think, I'm just going to do research for the rest of the time, and all of a sudden you discover, whoa, I'm really truly not.
Yeah.
But it comes out in other ways. I've got fabulous PhD students who are dealing extremely well with the pandemic, and they're doing my research for me, I guess. And, my ideas are becoming the basis for their PhD, and we're exploring things that way. So it's been I've been very fortunate, I would say. Astronomy is a cruel mistress, like all science. The number of PhD students, or undergraduates is a huge number, and PhD students are still quite a lot. And the numbers decrease, so then you don't have a huge number of positions for postdocs, and then you have even fewer positions for permanent jobs. So there's a huge, sort of every time there's a huge cut of people.
Yeah.
So I'm very lucky to end up where I have done, and it's been wonderful. Science is fantastic. It's cruel as well, but it's a good place to end up. So that's been my journey. Amazing.
So my next question is quite an involved question, but I suppose you can unpack it for us and tell us a bit about it and how it relates to your research on it. So what is spectral timing, and how does this relate to the changes in the accretion flow when it reaches and exceeds the classical Eddington limit?
Okay, so you need to strap in, right? Because this is we're going to have to unpack this one. So most of my work involves compact objects. So by compact objects, I mean gravitationally compact. So when a star dies, when a very high mass star dies, what happens is that its core can no longer support itself against its own self-gravity, its own mass. And so it all collapses down, and then the end product depends on how much mass there is. It can either be a neutron star, which is quite a complicated thing. It's incredibly dense, and there's some very interesting particle physics going on there. Or it can be a black hole. And those things would, then the rest of the outer bit of the star is completely lost through a supernova explosion. But typically, these black holes and neutron stars, they have a companion star. So our sun is weird, but it's not weird, but it's not common to have an isolated star. Typically, you have binaries or triple star systems. And so if you have a neutron star or black hole and you've got a binary left, a binary companion left, eventually they can become close enough that material can cross from the companion star to the compact object. And when it does so, it falls towards the compact object and turns gravitational potential energy into kinetic energy and heat. It does this through what we call an accretion disk. So think of like a thin frisbee, and in the center of that frisbee, you have a neutron star or a black hole. So that accretion disk is made up of gas, and it has what we call viscosity. So you've got lots of things rubbing together, and it gets very, very hot. In reality, actually, viscosity is the product of something called turbulence, but we won't go into that because you don't have time for that. And so this accretion disk gets very, very hot. And very close to the black hole or neutron star, it's hot enough to emit the X-rays. So what I tend to do is I use satellites that can observe in the X-rays. We can't do it from the ground because the atmosphere, thank goodness, protects us from X-rays. X-rays are quite mutagenic, and you don't want to be bathed in X-rays. That's why when you go to the doctors, they're mercifully brief. And so we have to use telescopes on these satellites in orbit around the Earth. And so what those telescopes tell us is not only how bright are these objects in the X-rays, but they tell us how bright they are at specific energies within our X-ray portion of the electromagnetic spectrum. If you then plotted how bright that is as a function of energy, you'd have a spectrum. So that's all that means. Now you can have spectra in the optical and the radio. All it is brightness as a function of energy. So that tells you a lot. You can learn about the temperature of the gas very close to the black hole and neutron star. You can learn about the geometry of the accretion disk. You can learn about, is it really a frisbee? Is the material being kicked off from the frisbee, which there is in what we call winds? You can learn about astrophysical jets. So this is material being spat out at close to the speed of light from close to the neutron star or black hole. And you can learn lots and lots and lots. And people have written entire books on these things. The other side of this is, how do these objects vary as a function of time? So how do they change? And the way in which things change can reveal huge amounts. So instead of having a picture, you have a movie, and the movie is always more interesting than the picture. Right? I mean, saying that, I love going to galleries, so that makes me sound like a hypocrite. You learn a lot more. As a great example, people looked at how rapidly things were varying in the very centers of galaxies, and from that they deduced there must be massive black holes within the centers of pretty much all galaxies. In the same way that there are these things called gamma ray bursts that vary over very short periods of time, so you can constrain how big they are. And that's just a simple example. So what I do is I combine our picture with our movie analogy. So I see how does the brightness as a function of energy change as a function of time. And by putting all that together, I'm able to learn a lot more about these systems. So really it is watching the movie and trying to learn whatever we can from it. And then you mentioned the Eddington limit. I mean, my goodness, this is the next bit, right? So there's this classical limit. So you can imagine that if you've got a star, let's say, and it's very, very bright, it's creating a lot of radiation in the form of photons. Those photons don't fly through stuff without interacting, typically. They can do to a certain distance, but typically they interact with stuff. A great example is if you put your hand to your eyes, you've not seen anything. The photons can't get through your hand, right?
So what you can imagine is that those photons are hitting things, and when you hit something, you give it a bit of a push, right? And that bit of a push is a force, right? It's creating a push. There's pressure, therefore there's a force. Now the other force you've got to take into account when you've got a star is gravity. Right? We all know about gravity. Gravity is the thing that keeps the moon going around the Earth. It's actually, technically, it's the curvature of space-time or whatever. And the gravity of our sun is quite immense. So what you've got is the outward push for these photons that they try to get out of the star, and this inward pull of gravity. Now, when those things are balanced, due to the amount of radiation that's coming from a star, that's when we reach what we call the Eddington limit.
Okay.
And the Eddington limit is only appropriate for where you've got a spherical system. Now, when you've got a frisbee, an accretion disk, the spherical limit doesn't really work anymore. And what I'm particularly interested in is how does the frisbee, the accretion disk, change when we get around the Eddington limit? Because it's still relatively important in some regards. And that area of physics, that area of accretion physics, is really important because when in the very early universe, after sort of less than 1 billion years, black holes, like, you know, we've got supermassive black holes in the centers of galaxies. Some of those were already fully grown after a very short period of time. And the way that black holes grow is they eat material. So they gobble all this material and they get big, which is just clearly a metaphor for my life in lockdown. And so they eat and eat and eat and eat and eat and eat, and they get bigger and bigger and bigger. And they're eating at such a rate that their frisbees, their accretion disks, must have been above this Eddington limit as we define it with a spin. So by understanding what happens, hopefully I can understand what happens in the early universe, which then dictates everything that's happened since in terms of the evolution of galaxies and stuff like this. So does that just about answer your question, Martha? I went about all the houses then.
No, that's amazing. That's brilliant. So you mentioned the X-rays that are sort of emitted by black holes. So as materials spiral into the black holes, these X-rays are emitted, and they echo and reverberate as they interact with a nearby gas. So you use the European Space Agency's observatory, XMM Newton, to do the longest observation of an accreting black hole ever taken with this observatory, which was 16 full spacecraft orbits over 23 days, to track these X-rays from a black hole named Iris 132243809. So these echoes changed as the corona's size changed. And so how was this beneficial for you?
Right. Again, some unpacking here, I feel. So these were a set of observations by XMM Newton. So XMM stands for X-ray multi-mission. It's multi-mirror. It's one of the most important workhorses in the X-ray astronomy arsenal, along with Chandra and U-star and others. And Andy Fabian, Professor Andy Fabian, received a huge amount of time to study this AGN called IRAS 13224. One of the things about astronomy is they're full of telephone number objects. You very quickly go, what? The first bit tells you the instrument that detected it, and then the rest tells you some other things. Not typically the location in the sky, which makes it all bit boring actually. So IRAS 13224 is one of these supermassive black holes in the centers of the galaxy, and it's producing a huge amount of X-rays because of this frisbee. So it's all these X-rays are coming out. And the thing about IRAS 13224 is that it varies a lot over time. So remember I was telling you about how we can study how things, we can go from a picture to having a movie. Well, the movie is a very exciting thing in IRAS 13224 because things are changing a lot. And that means that we can look for changes much more easily. Because if it's changing a lot, then you can say, oh, okay, I can see how things are changing in between, and I can get a much better, higher definition movie, if you like. So some of this work has been led by various different people within that group. Dr. Lawson in particular put out a very interesting paper where we're talking about how the geometry of the accretion flow near the black hole is changing as a function of time. Now, I've told you about the frisbee, because that was a nice, simple analogy. Now, in reality, the frisbee's got a friend, and that friend's called a corona. So all a corona is
is a bunch of really hot electrons. You know what electrons are, subatomic particles. And these electrons are living in a gas somewhere near the black hole. And one of the models is called the lamppost model, and this postulates that this corona is probably the base of one of these jets, which is being spat out close to the speed of light, and it's sitting quite close to the black hole. Now, what we were able to deduce from these observations was that the corona was actually moving around. So what happens is that the corona is full of hot electrons. Those electrons see the frisbee, and the frisbee is producing photons, radiating emission. Those photons hit my friend the corona, and then some very interesting physics happens, and those photons change their energy. They actually gain energy from the electrons, because the electrons are very, 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 very energetic and very excited. The photons are feeling a bit dopey, a bit sort of slow. They gain some of their energy from the electrons, and then they bugger off. So they gain energy. And then what we can do is look at how those now more highly energetic photons then irradiate the frisbee. So it works in two ways. The photons come from the frisbee, hit the corona, gain energy, then go and then re-irradiate the frisbee. It's quite complicated, but hopefully you get the idea. And so from modeling how our spectrum, so our brightness is a function of time, brightness is a function of energy changed as a function of time, Will was able to deduce that this corona was moving up and down. And this is kind of really cool, because you've obviously seen the pictures from the Event Horizon Telescope and the pictures of M87. We can't do that for most systems. We can get very high resolution images for the center of our galaxy, Sagittarius A star, although it's really complicated. That's a really, really difficult part of the galaxy to look at. There's a lot of stuff going on. And M87, you can't do that for most AGN. They're just too far away. So the only real way to get an understanding of what does the inner region look like is by doing this thing called reverberation. So the corona changes, and then we see everything else change afterwards. And the reason it changes later is because it takes light a certain time to travel from point A to point B. Right? Everyone knows the speed of light is constant. So you can then use this idea to then work out what the geometry of this flow looks like. Does that kind of get that?
Amazing, yeah, absolutely.
Brilliant.
Using this reverberation, as you said, you can then obtain an independent timing-based estimate, but for the mass and the spin of the black hole. So what's your goal in terms of measuring this for many black holes and overcoming current technological issues in methods used?
So there are, you may never have heard of this phrase because you're still in school, essentially still sixth form, but black holes have no hair. Which sounds a bit, I don't know, almost a bit cruel. You know, nothing against the people with alopecia. It's just, or male pattern baldness. But what they mean by that is that black holes, astrophysical black holes, can only be defined by two quantities: their mass and their spin. Now, it's quite difficult to imagine a black hole spinning, because really the way to imagine a black hole is just extreme curvature of space-time, which is a very different conversation altogether. The other quantity which has been postulated is charge, and then you have what's called a Kerr-Newman black hole. But in reality, astrophysical settings are so full of charged particles that your black hole will become neutral very quickly. So we think really it is just mass and spin that defines everything about a black hole.
Okay.
Now, the other thing about black holes is when I said that they grow by gobbling material. They can also grow if two black holes come together. And we've seen beautiful evidence for that from the recent detection of a black hole merger with LIGO, the gravitational wave interferometer. So black holes can grow that way too. And then what changes is your mass, but also your spin. So what we're interested in is looking at the mass and the spin of black holes, and then trying to work out how do they grow over cosmic time. So this really goes back to what I was saying about the very early universe and the fact that we need to invoke some extreme physics to explain their growth. So it's all interconnected. It's all about trying to be cosmic historians and trying to understand what happened then, and try and improve our understanding of really how the universe looks and why.
Fascinating. So can you talk to us a little bit about ultraluminous X-ray source populations? So you've done about the relative number of these compared to black hole primaries using geometrical beaming, and then you've also done sort of the ratios of these in terms of their age and other factors as well. So can you talk to us a little bit about these?
Absolutely. Okay, so ultra-luminous X-ray sources, or ULXs, came about when in the 1970s we started launching X-ray satellites. And we discovered that, I say we, I was around in the 1970s, I'm way too young for that. We discovered that there were these X-ray bright sources in other galaxies, but they weren't associated with a central bit, which is where you would find your supermassive black hole and you would describe it as an active galactic nucleus, or AGN. And thus the term ULX was born, ultra meaning the most bright that you can get. Now, unbeknownst to us, actually there were brighter sources, so that was a bit of a problem because there was nowhere to really go with the definition. So hyperluminous X-ray sources, and heaven forbid we find an even brighter class, because then we're really screwed. I don't know where we go with that, like mega wicked luminous sources, I don't know. So for a long time the debate raged as to what these things were. And there were two different sides to this argument, as there often are. One postulated that ULXs contain what we call intermediate mass black holes. So we have stellar mass black holes, which can be up to maybe 30 times the mass of the sun, and we have supermassive black holes, which are typically above 100,000 times the mass of the sun, up to billions or tens of billions. They're really huge. So intermediate mass black holes are supposed to fill in that gap. Now we know that intermediate mass black holes technically exist because we know that from the LIGO result that two black holes came together, they merged and created something bigger. We also know that in the centers of dwarf galaxies, so these are small galaxies, there should also be supermassive black holes, which are fairly massive. So people postulated, okay, these are intermediate mass black holes. Now, myself and others said, actually, what probably is happening is that we're seeing this frisbee, an accretion disk, get to the Eddington limit and then change its nature. So what happens is that when you get around the Eddington limit, you're still producing a huge number of photons, so you're still producing a lot of radiation, and it means that your frisbee isn't thin anymore, it's really thick. So you have to imagine that this thing ends up actually looking like a cone like this. So that's when it's not a very high mass accretion rate, and that's when it's a very high mass accretion rate. Okay. So what happens with an ultra-luminous X-ray source, if it looks like that, is that you've got a cone. And then the way this cone operates is a little bit like a car headlight. So, and I don't recommend you do this, but if you took out the bulb from your car, or your parents' car, depending on how vicious and evil a child you are, and just looked at it, it wouldn't look particularly bright. The reason it looks bright in a car headlight is because it's wrapped with mirrors. So all the light bounces off the headlight from the lamp and then comes towards you. And the same is kind of true with ULXs, that if you've got this cone and then a very bright X-ray source at the bottom of that cone, it looks really, really super bright. And so that was the idea. And then in 2014, we had unambiguous evidence that ULXs definitely contain neutron stars. Now, they don't necessarily all need to contain neutron stars. And in fact, if you look at how the populations of binaries should evolve, there should be some that contain black holes and some that contain neutron stars. But the problem in the field at the minute is trying to work out exactly how many of each there should be. Why is that important? Well, besides the fact that it satisfies our curiosity, the numbers tell us about how binary systems evolve. So we have models that say this is how many neutron stars there should be, this is how many black holes there should be. And those same models are used to predict how many gravitational wave sources there should be. The same models are used to understand how the universe at very early times was irradiated by all of this radiation and produced something called the epoch of recombination and the epoch of reionization. So there's lots of different things that go into this. Sorry, not the epoch of recombination, I meant the epoch of reionization, EOR. So going back to the ultra-luminous X-ray sources, that's the game now, is to understand how many neutron stars there are, how many black holes there are. And this thing where I wrapped my X-ray source around in a mirror and beamed it at you, that is called geometrical beaming. Okay, and you can imagine that if my cone is pointed away, I can't see anything. Right? And it's pointing towards me or you, it's really, really bright. And so that is what we think ULXs are. There's this huge range of sources, some edge on, some face on. And so the game is, can we use those properties to understand where the black holes are, where the neutron stars are?
Amazing. So you calculated the mass loss rate due to the wind in ULX pulses, which is accounting for the neutron star magnetic field strength and advection processes in the disk. So can you tell us a bit more about this?
Okay, which paper was that one? Do you know which one it was? Because I don't. Was it one that was Me's first one, or was it somebody else?
I will link it on the side of the podcast.
Brilliant. Okay, because so there's been a lot of work recently trying to understand the true nature of these things. It could well be that this was when I was writing my, so I've recently published a theory about how the inner regions of these things might wobble around due to an effect of general relativity called length theory of recession. And that's related to the mass loss rate due to wind, so maybe it's connected to that. Okay, so this is even more complicated than the stuff I mentioned before. So you take, you really got down the rabbit hole now. So you've got your now very, very thick accretion disk. You've gone from your frisbee to something like this. Now, actually, the radiation that these things produce, they can be produced actually quite close to the mid-plane of this very thick disk, and it takes photons a long time to get out. Right? They've got to get to here before they can escape. And it's possible that by the time it takes for our photon in the middle to get out of our cone is actually longer than the time it takes to be sucked into the black hole, essentially. Black holes don't really suck, but it falls into the black hole. That's called advection. So it's basically swallowing the energy without letting it get out. So that's an important consideration in all sorts of accretion. Then you've got winds. So winds are basically material that's being driven off our accretion disk from our frisbee, or from our very thick frisbee. And so what you have to do if you want to really understand these systems is understand how much mass is lost in these winds. So it's a bit like getting a fan and like blowing dust off your desk. Right? That's what a wind is. The dust is being blown off. Right? It should go away. We should all clean our desks. As I look around and see the nightmare that is my desk. Because you've got material which is being kicked off in a wind, and then you've got this advection. And if you put those things together, that really gives you a clearer picture of how much material gets onto your black hole or onto your neutron star. So it's a really important quantity that we don't have a great handle on advection. We have a much better understanding of winds. And the reason for that is that this material that gets thrown off, it provides basically a curtain. And we can see actually through some of that curtain. It's not a thick curtain, we can perceive some of the stuff behind it. And what we look for is atomic transitions. So you ought to be a biochemist, so you know all about atomic transitions, right? So your radiation excites bound electrons within your atom, and so we see those photons aren't present in the spectrum that comes through. And because the wind is moving, there's this effect called Doppler shift, and so our absorption lines actually shift energy. So we can put all this together, and then we can first of all show that there are winds, which was a huge step forward. We speculated back in 2014 that the things that we were seeing in the energy spectrum of ULXs were winds. We confirmed that in 2016, and now there's this industry of finding these winds in ULXs and understanding them. So we can now better understand these winds. So that's a big tick. But understanding advection is considerably more complex. And how that fits into pulsars, well, my goodness, that is very difficult indeed. We could talk for hours and try and work that out. I'll save you the agony of that.
No, that's wonderful. So I guess a more general question is, what could be your hopes for the future in terms of sort of advancements in technology surrounding this area, or what you might want to research next?
So my hopes for the future, great. I hope we have people like you coming into science. I think that'd be wonderful. I don't think I can lay away from the joys of biochemistry, but astronomy is a fantastic thing to get into. I want people to embrace science as much as they can. Even if you don't want to become a scientist, it's really important to have a scientific education.
Even if it isn't about the maths, even if you're confident about the maths, try and seek out some level of science, because you're learning about the universe and about the world. If you want to be in the world, you need to understand it. If you want to function in that world, you need to understand it. Science is a crucial part of that. In terms of where do I see my personal field going and my research going, there are some really important satellites being launched in the near future. The James Webb Space Telescope is perhaps the most obvious one. I would love to see the development of advanced technology so we can better understand these systems, but that's very expensive, really expensive. We also have something coming along soon called the Vera Rubin Observatory, and it's doing this survey. And this survey is going to be one of the most groundbreaking things that's ever happened. So looking at a huge portion of the sky with a really sensitive ground-based optical telescope, and the numbers of events that we expect to get per night are something like 100,000 to 1 million.
Oh wow!
Then yeah, exactly. And then you've got a real problem on your hands, because you then need to understand, what do I look at? I've got too many options. So a really important direction that modern science is going in is incorporating artificial intelligence or machine learning. People love to say artificial intelligence because it evokes things of, like robots and stuff. It's not that at all. Machine learning is essentially just a set of algorithms that allows you to learn what an interesting object is from a whole bunch of objects. And so my interest is really actually pushing that in a certain direction to find a certain type of object. And the thing that I'm really interested in finding are these hidden black holes and neutron stars in our galaxy, of which we predict there could be huge numbers. We know of about 60 black holes in our galaxy, and there should be hundreds and hundreds of thousands, maybe even millions. Now that might freak you out. I don't want to give any listeners a sleepless night, but those things are wandering around, coming to get you. But I've got designs on trying to find these things using various techniques. And that's basically, I think the other thing that I really hope for the future is that, and I'm not going to put on my RAS hat or anything here, but in terms of the way we fund science, I think there's a real, sorry for that noise, that was my PhD student contacted me on Sunday. The way we fund science, we need to make sure that it isn't all about industry. It's really important to push our industry, especially in the minute we need to make sure our economy is fit for purpose. But blue skies research and open, take away the ceiling, blue skies research is really important, because you never know what you'll find. And so I've got lots of hopes for the future. I don't know if any of them will come to pass. But it's a wonderful thing to be involved with science, and I encourage you and all of your listeners to get involved as well.
Absolutely. Well, thank you so much. I've really enjoyed this.
My absolute pleasure, Martha. It's been great. It's been wonderful chatting to you about the things that I love doing. So I'm glad you've enjoyed it. Absolutely,
yeah. So hopefully people have enjoyed this as well, and I've linked all the papers that I've referenced by the side of this podcast. So thank you everyone for listening, and I'll see you next time.